maybe one example. So let's say we have a line 7x plus 8y equal to 9, and it passes through the point. What have I got here? Negative 4 7. Oh, that's a gross point. Okay. Negative 4 7ths, comma 15 19ths. That is not the nicest point ever. Now I want to point out that this point isn't a point on this line. Our line is either parallel to this or perpendicular. So it's going to be two different problems. And each of these lines, the parallel one to this and perpendicular one to this, pass through this point. So our job is to find the equation of the parallel line and the perpendicular line. And in either case, we have to find the slope of this line. And to find the slope of this line, we have to isolate y. I mean, there's probably other ways you could do it, but the easiest way is to say, okay, well, I'm going to solve for y. So 8y equals negative 7x plus 9. And then dividing both sides by 8, I get y equal to negative 7/8 x plus 9/8. Then we can say, oh, look, that's the slope of that line. So for this line that's parallel, our slope is going to be negative 7/8. And the point is this gnarly looking point here, negative 4 7ths, comma 15 19ths. For the perpendicular line, the slope is the opposite reciprocal. So instead of being negative 7/8, it's going to be positive 8 7ths. But the point's still the same point, negative 4 7ths, comma 15 19ths. So if I'm going to find the equation of this line, I'm going to use the point slope form. Sorry, yeah, point slope. Saying y minus the y coordinate is equal to the slope times x minus the x coordinate. And if I could, I would leave it like that, right? If we're allowed to, I think it's nice to just say we're done. A lot of the times we're not. A lot of times we actually have to solve for y and write it in the slope intercept form. So if I was solving for y, I would distribute the negative 7/8. So negative 7/8 times x is negative 7/8 x. And negative 7/8 times positive 4 7ths, the 7ths will cancel, and you'll get a negative 4/8, which will be 1/2. And it is negative because it's a negative times a positive. And then we would add 15 19ths and get y equal to negative 7/8 x minus 1/2 plus 15 19ths. Then you have to get like a common denominator, add those together. This is going to be 19 over 38. I should say negative 19 over 38. It's going to be positive 30 over 38. So that's going to end up being 11 over 38. So that's what we get for the parallel line. Negative 7/8 x plus 11 over 38. Not very nice numbers, but the process is pretty familiar. I keep looking at my pens now, like, which of these? A lot of these are like super empty. I thought I refilled them all. Maybe I didn't. Yeah, you guys are. I think I'm trying to get these ones to be empty so that I can refill them. For this one here, it's the same process. So now we're going to plug in 8 7ths there. But it's still going to be y minus the y coordinate equal to 8 7ths times x minus the x coordinate, which I'm just going to write as plus 4 7ths. And then we would do the same thing. We would distribute the 8 7ths. Y minus 15 19ths equals 8 7ths x. And then 8 7ths times 4 7ths is going to be 32 49ths. Ugh. And then I'm not going to finish this one exactly. We would get y equal to 8 7ths x plus 32 49ths plus 15 19ths. And then I guess you should add these together by getting a common denominator, which is going to be fairly gnarly. But that's how you do a problem like this. Great. Let me check that off my list. I just want to go over the couple like earlier stuff that people asked me about before we get to the next stuff. So the other one, couple had questions about some domain and range things. Let's look at a couple examples here. Yeah. Oh, yeah. I got it. I know exactly what I'm going to do. So yeah, and then some inverse function stuff. Let's look at this. So one question somebody asked me was if f of x is is equal to 6x minus 3, and g of x equals to, where'd it go? X plus 3 over 6. Find f of g of x and g of f of x. Now this question specifically is supposed to get at the point that shows us that f and g are actually inverse functions. So if we look at f of g of x, there's a couple ways people write this. I typically like to work from the inside out. I mean, I usually write this as f of x plus 3 over 6. And then say, okay, f is 6x minus 3. So that's going to be 6 times your input minus 3. Some people like to kind of go the other way, meaning they would write f of g of x as, well, f of x is 6x minus 3. So f of g of x is 6 times g of x minus 3. And then g of x is x plus 3 over 6. That's going to be 6 times x plus 3 over 6. And hopefully you all can see that no matter which way you think of it, it's still the same thing. You still end up with the same exact expression at the end. And then we can cancel some stuff. The 6's cancel, and you get x plus 3 minus 3. And then the 3's cancel, and you get x. And then if we did g of f of x, the same sort of thing would happen. G of f of x is g of 6x minus 3, which is equal to g, no, not g, I'm not going to write g of anymore. So I know that g of x is x plus 3 over 6. So g of some stuff is some stuff plus 3 over 6. And then the stuff is this stuff here. And then the 3's cancel. So you get 6x over 6. And then these 6's cancel. And you get just x. The weirdest looking x I've drawn in a while. And so then, not that the question asked this, but this does tell us that since f of g of x and g of f of x both equal x, right, we got that f of g of x equals g of f of x equals x, right? Usually the reverse order of composing functions isn't the same. Right? Usually f of g of x and g of x are not the same, but when they are the same and equal to x, this means that f and g are inverse functions. They undo each other, right? F does something and then g undoes it. So like f of 2, for example, f of 2 is 6 times 2 minus 3, which is 9. And then g of 9 is 9 plus 3 over 6, which is 2. So f does something and then g undoes it. That's the whole idea with inverse functions. And then to kind of piggyback on that, that's a good question here to ask. Sure, that's a good question. What's the, what's the domain and range of f of x equal to e to the x plus 5? Oh, interesting question. So we can either find, well, the domain is really straightforward. The domain here, I don't see any of the typical 3 problems, right? There's no square roots, there's no logarithms, there's no division by anything possibly 0. So here the domain is everything. All real numbers from negative infinity to infinity. The range, on the other hand, so we could find the range graphically, but I would rather find it analytically. I'd rather find the domain of the inverse. For those of you that are wanting to see limits, don't worry, we're going to get into limits very shortly. I just want to kind of wrap up these last few things here. So to find the domain of the inverse, so we have to find the inverse. So I'm going to write y equal to e to the x plus 5. And I'm going to try and, well, I'm going to switch x and y. So x equals e to the y plus 5. So then you might observe here, well, look, x can't be negative, x can't be anything less than 5 because e to the y is always positive. plus 5 is going to be even more positive. But we're going to do it the normal way, the more standard way, I guess, by solving for y. So subtract 5, x minus 5 equals e to the y. And then we're going to take the natural log of both sides. So that the natural log of x minus 5 equals y. So our inverse function, f inverse of x, is the natural log of x minus 5. And we know that for a function with a logarithm, the stuff inside the logarithm has to be greater than 0. So our domain here of f inverse of x, we need that the inside of the logarithm is greater than 0, which means that x is greater than 5. But the domain of the inverse is the same as the range of the original function. So the range here has to be bigger than 5. So everything from 5 to infinity, not including 5. You could also have seen this graphically. If you graph e to the x plus 5, it's just the e to the x function shifted up 5. E to the x usually has a horizontal asymptote at 0. So if we shift it up 5, the horizontal asymptote is now at 5. And it looks kind of like this. So you can see, oh yeah, the range, we don't get anything equal to or less than 5. So the range is everything above 5. That's another way to see it. Oh, yeah. People had some domain questions. Let's look at a couple more domain, and then we'll get going on to all the limits and the asymptotes. Yeah. Someone asked about domain with roots. And I wasn't exactly sure what they meant, but I think I have an idea. So let's take a look at these two questions that are kind of similar, but not quite the same. So I'm interested in finding the domain of the following two functions. I want to find the domain of 1, f of x equal to, what do we got here? 3 over x squared minus 7x. And 2, g of x equal to the square root of x squared plus 7x. Oh, sorry, minus 7x. So in both of these cases, we're dealing, the x squared minus 7x is kind of the problematic part, but there's different requirements in each of these cases, right? For the first one, we need x squared minus 7x to not equal 0. Or what I usually like to write is we need to exclude where x squared minus 7x is equal to 0. I forgot there was also a bunch of questions people sent me. I thought that's cool. I think we're good. See one thing, sorry. Oh yeah, we're fine. Cool. Yeah, those are way. Definitely got all the screenshots people sent me, and we'll get to those too. If not today, then certainly Thursday. So here we're excluding this. On the other hand, here we want the insides to be greater than or equal to 0. Both of these problems really require us to figure out where it's equal to 0. So in either case, I'm going to factor. I get x times x minus 7 equal to 0. So I get x equal to 0 and x equal to 7. And in this problem, those are the only points I want to exclude. So if I've got 0 and 7, I don't want those, but I literally want every other number. I want all of this, I want all of this, I want all of this. So here my domain ends up being everything from negative infinity to 0, union 0 to 7, union 7 to infinity. And I will say that typically when you have a domain question and it's just something that's fractional with no square roots or logarithms, you're typically just picking out some finite number of points from the entire interval. So here I'm getting the entire real number line except for 2 points. Whereas when you have a square root or a logarithm, you're typically removing a whole section. So here I'm going to again look at the same points. I know that 0 and 7 are where this is equal to 0 because I just did the work over there. And I know I want to include those points. Right, so that's one of the differences here. I actually want those points here because they make it equal to 0. And then I want to figure out where it's greater than 0. So I pick numbers. I pick something like 8. I probably should factor this. This is x times x minus 7. So if I pick 8, then I can see that 8 times 8 minus 7 is a positive times a positive. And if I pick something like 2, 2 times 2 minus 7 is a positive times a negative. And I pick something like -1. -1 times -1 minus 7 is a negative times a negative, which is positive. So I want this region and I want this region where it's positive, greater than 0. So here in my domain, I'm missing this section here. But I want everything from minus infinity to 0, whoops, inclusive, so a bracket, union bracket 7 to infinity. But I'm missing that whole middle part there. And then, yeah, let me see. That seems good. Okay. Oops. Sorry, I just want to check a few things. Yeah, okay, sure. People had questions about limits, and there's kind of a lot of stuff with limits. So let me grab something here. Yeah, limits are tough. So last time we talked about kind of lots of different limits that were 0 over 0 types. And I know that we're getting into limits to infinity and limits that are equal to infinity, which is also something that we want to have. Yeah, sure. I think we can wait on you. Sorry, one moment. I'm just trying to make sure I do things in kind of a reasonable order. Let me see. Yeah, okay, so let's do that. Is there going to be anything to show that there's going to be 3? Oh, for sure, Lauren. So for example, so I think it's a good question. Ow, pinch my finger just a little bit. It's really fine, but almost caught my finger in the board there. You can have a lot of intervals. For example, I could ask a question like, what's the domain of f of x equal to the square root of, what have we got here? Let's do, sorry, I'm trying to think of something that's going to work out nice. Sure. 8 minus x to the third times x minus 5 times, sorry, it's going to be kind of long, times x plus 1 squared. I don't know. I'm down a bit. Sure. Sorry, this one's a little contrived, but I think this will get at the idea here. So here's a question someone could ask if they want to. So find the domain of f of x equal to the square root of 8 minus x cubed times x minus 5 times x plus 1 squared times x plus 2 times x plus 5 cubed. So for any kind of domain question like this, you always want to put on the number line all of your zeros, all of the things that make the inside equal to 0. Here, it's pretty obvious it's going to be positive 8, positive 5, negative 1, negative 2, and negative 5. So there's a lot of potential intervals here. And we might only get 2 still because I might not have designed the problem super well. But it's okay, even if we only get 2. So if we pick a number larger than 8, like 9, 8 minus 9. So, and again, I guess I should write out. We're trying to solve this inequality. 8 minus x cubed times x minus 5 times x plus 1 squared times x plus 2 times x plus 5 to the third greater than or equal to 0. So picking a number larger than 8, 8 minus 9 is negative. 8 minus 5 is positive, 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 positive. So I have a negative times a bunch of positives, so it's going to be negative. And then I pick a number between 5 and 8, like 6. 8 minus 6 is positive, 6 minus 5 is positive, 6 plus 1 is positive, 6 plus 2 is positive, right? Everything's positive. Now, it gets kind of tiresome to keep doing this plugging in anything. So another way you can actually think about what the sign's going to be is start over here, like we did, and then look at 8. 8 came from a factor with an odd power, which means the sign is going to change. 5 came from this factor that also has an odd power, which means the sign is going to change. You could also pick a number and check that, right? If you pick 1, 8 minus 1 is positive, 1 minus 5 is negative, 1 plus 1 is positive, 1 plus 2 is positive, 1 plus 5 is positive. So it's a negative times a bunch of positive, which is negative. And then negative 1 came from this factor here, which has an even power, which means the sign is going to stay the same. Or we could pick a number in between negative 1 and negative 2, which is kind of a pain, right? If you pick like negative 1.5, 8 minus a negative is positive. Negative 1.5 minus 5 is negative. Negative 1.5 plus 1 is negative, but the negative number squared is positive. And then negative 1.5 plus 2 is positive. Negative 1.5 plus 5 is positive. So overall, a negative 1.5 is still a negative overall because of the negative right there. And then negative 2, which came from this factor, it's going to change because it's to an odd power. At negative 5, which came from this factor, it's going to change signs again. So here would be my interval. I want all the endpoints. Oh, this one has kind of a funky answer. So my interval would be, or my domain would be, the interval from negative 5 to negative 2, because I want that part. And then I don't want anything from negative 2 to 5, except I want the single to negative 1. And it's typically written as something with braces, where you just contain the one number. And then you want everything from 5 to 8. But hopefully you can see like how if you have a bunch of different places where it's 0, it's certainly possible to get any number of intervals, right? You can get 3, you get 4, right? You could literally have really any possible number of intervals. Right. Erase the backside here. I know someone had a question about. Let's talk more about limits. Can you go over the negative 1 again? Like why we include that? Okay, so is negative 1 in the domain? Well, if I plug in negative 1, I get 9 times negative 6 times 0 times, it doesn't matter what the rest of it is, because once one of the factors is 0, the whole product is 0. So when I plug in negative 1, I get 0. And the square root of 0 is perfectly okay. Square root of 0 is 0, right? So that's why we're including the negative 1. It's the same reason we're including all of the endpoints here as well, right? It's the same reason we're including negative 5 and negative 2 with a bracket and 5 and 8 with a bracket. It's just that since negative 1 is the only point in this interval, right? We don't want anything to the left or to the right. We write it this special kind of way with braces. Okay. Yeah, let's look more at some limits. So I think, yeah, let's just jump straight into the limits. So last time we did all the 0 over 0 limits. So let's do 1 or 2 of them just to kind of refresh our memories. Let's say I want to take the limit as x approaches 5 of 2x minus the square root of, that's sure, 95 plus x over x minus 5. Okay, so I really want to remind everybody, when you're finding a limit, we don't actually care what's happening at 5, right? If you plug in 5, you're going to get 0 over 0. You're going to get 10 minus the square root of 100, which is 10 minus 10. And the bottom, you're going to get 5 minus 5. So if you get 0 over 0, that means we have to do some more work. 0 over 0 is never the answer that we end with. In this case, we're going to multiply by the conjugate. 2x plus the square root of 95 plus x over the same thing. My goal is always to do as little multiplying out as possible. I don't want to multiply out these terms because I know I want this x minus 5 to cancel. But I do want to multiply out these terms. So I'm going to rewrite this as the limit as x goes to 5 of 2x times 2x is 4x squared. The middle terms cancel. That's why we multiply by the conjugate. And then the minus square root of 95 plus x times the positive square root of 95 plus x is going to be minus 95 plus x. This is going to be interesting. Well, it's okay. I think I know what's supposed to happen, so it should work out all right. I hope. And then on the bottom, we have x minus 5 times 2x plus the square root of 95 plus x. Okay, I'm going to rewrite the top just a tiny bit. I'm going to rewrite it as 4x squared minus x minus 95. And here's the thing. I don't know how this factors, but I'm pretty sure it's supposed to factor. Because I know if I plug in 5, I get 0. Let's double check. If I plug in 5, I get 4 times 25, which is 0. Sorry. Wow. 4 times 25 is 100. Minus 5 is 95. Minus 95 is 0. If I plug in 5 in the bottom, I get 0 times it doesn't matter. So I still have a 0 over 0 type, right? If I haven't canceled anything yet, I haven't changed from being a 0 over 0 yet. But here's what that tells me. If I plug in 5 and the numerator is 0, that tells me that I should be able to factor out an x minus 5 from the numerator. Right? There's no question. And here's the thing. If x minus 5 is a factor and it has to multiply to 4x squared minus 95, well, I have to have a 4x. So that x times 4x is 4x squared. And I have to have, let's see, 95 divided by 5 is 19. So I have to have a plus 19 here. There's no other way it could factor. Let's double check. X times 4x is 4x squared. Minus 5 times 19 is minus 95. And 19 times x is 19x. Minus 5 times 4x is minus 20x. And minus 20x plus 19x does give me a minus x as the middle term. So if you know that something's supposed to come out as a factor, it makes factoring a quadratic actually kind of straightforward. Then we cancel the x minus 5s, and we plug in 5 for the rest of the x's. So to actually find the limit, you have to plug in what x is approaching when you can. So I'm going to plug in 5 here and get 4 times 5 plus 19 over 2 times 5 plus the square root of 95 plus 5, which then simplifies as, let's see, 20 plus 19 is 39. Over 10 plus 10 is 20. That would be our answer. Okay. I try to leave the board up while I erase the back so you guys can look at things, see if you have any questions. Seems to be a good method of operating. But as you've probably seen by now, 0 over 0 limits are not the only kinds of limits we encounter. Yeah, let's talk about limits to infinity, and then we'll talk about limits that end up equaling infinity. I feel like I'm forgetting something important. Oh yeah, I know what we're gonna do. So yeah, actually let's kind of hit them both at once. So I think this is a good question to start with. I want to find the horizontal and vertical asymptotes of the following function. F of x equal to x squared minus 9x over x squared minus 6x plus 8. This is definitely a question from one of the classes that somebody asked me about. And the way I would say this is, I mean, there's a lot of ways to kind of think about this, but here are the general ideas. You get a vertical asymptote. I should say, really, technically, there's two ways to get the vertical asymptote. One of them is very specifically with a natural log or any logarithmic function, you get a vertical asymptote when the argument's 0. So that's kind of the special exception. You know, y equals log base b of x. You have a vertical asymptote when x equals 0. Aside from that one function, the only other time you get a vertical asymptote is when you have a non-zero number divided by 0. So typically, when I'm trying to find a vertical asymptote, I'm looking to see where is the denominator 0 and also the numerator should not be 0. And I'll show you a couple of examples of that. So to find the vertical asymptotes, the real answer is factor. So if I factor this, so f of x equals, let's see, if I factor the numerator, it's x times x minus 9. If I factor the denominator, it's x minus 4 times x minus 2. And then if anything canceled, I should cancel it out. Nothing cancels here. So then the easy kind of way to say this is we have vertical asymptotes where the denominator is 0. So we're going to have a vertical asymptote when x is equal to 4 and x is equal to 2. Now I should say there's more to this than just that. Because really the definition of having a vertical asymptote is that if you have a vertical asymptote at 4, it means that the limit as x approaches 4 from either side has to be some sort of infinity. Or I should say from at least one side has to be some sort of infinity. So let's look at the one-sided limits. If I look at the limit as x approaches 4 from the right of this expression, x times x minus 9 over x minus 4 times x plus 2. Sorry, minus 2. So if we plugged in 4, we get, let's see, 4 times 4 minus 9 is 4 times negative 5. So I get negative 20 on top. And the bottom, we'd clearly get 0, right? 4 minus 4 is 0. 4 minus 2 is 2. 0 times 2 is 0. So here's the question. What kind, and now this is going to sound like a dumb question at first, but just bear with me. What kind of 0 do we have in the denominator? Well, what I mean by what kind of 0 is the denominator slightly positive or slightly negative? So 4 minus 2 is positive. 4 minus 4 is 0, and 0 is neither positive nor negative. But really, it's actually not 4 minus 4. It's a number that's slightly bigger than 4, because we're approaching 4 from the right side of 4, which is the bigger than 4 side of 4. So if I have a number slightly bigger than 4 minus 4, it's going to be slightly positive, which I like to write as a 0 with a positive superscript like that, to think of the right side of 0 or the positive side of 0. So that the little plus superscript there just means we are on the side of 0 or the side of whatever number that's a little bit bigger than that number. So this means we're a little bit bigger than 4, like 4.00001. This means we're a little bit bigger than 0, like 0.0001. But what this means really is that we have a negative number divided by a positive number, which means it's going to be negative overall. I'm writing, the quotations are kind of around the whole fraction here. And the reason I'm writing quotations there is because, right, technically something divided by 0 isn't defined. So this is kind of the notation I and some of my coworkers use to kind of get around that. Sometimes we may write this. So here's what I know. I have a negative number divided by a very small positive number. So like if I did negative 20, so just to kind of make sure this is clear for everybody before we get to the final answer here. I'm gonna write it up here. If I had negative 20 divided by 1/1000th, but when you divide by a small number or divide by a fraction, you flip and multiply, that's going to equal negative 20 times 1,000 over 1, which is negative 20,000. And hopefully you can see that if the number was even smaller, the fraction would be even more largely negative. So that this ends up being negative infinity. And the general kind of idea is that if you're finding a limit and it ends up being a non-zero number over 0, it's got to be some sort of infinity, either positive infinity or negative infinity. And the way we find out is we just check the signs. If it's a negative overall, it's negative infinity. If it's a positive overall, it's positive infinity. So yeah, let me then, so just to kind of continue with this idea, let me show you that the limit, yeah, I can erase this top part too. Then we can also see the limit as x approaches 4 from the left. So now we're slightly smaller than 4 of x times x minus 9 over x minus 4 times x minus 2. That's equal to, well, again, I'm thinking of doing the same thing. I'm plugging in 4. 4 times negative 5 is still negative 20. But now the denominator, a number slightly smaller than 4 minus 4, is a number that's slightly negative. 4 minus 2 is still 2. I didn't write the 2 in there last time. I suppose I could have written the 2 in there this time, right? It doesn't change the fact that 0 times 2 is still 0, or a very small number times 2 is still a very small number. So now we have a negative divided by a negative. And a negative divided by a negative is going to be a positive. So the limit as x approaches 4 from the right is negative infinity. The limit as x approaches 4 from the left is positive infinity. And since the infinities are different types of infinities, we would say that the limit as x approaches 4 overall, or the double-sided limit of x times x minus 9 over x minus 4 times x minus 2, we would say that this limit does not exist because the left limit and the right-hand side limit are not the same. If they were both infinity or negative, both negative infinity, then we would say that the double-sided limit was also whatever the same value was. But since they're different, it doesn't exist. And the same would be true for 2. So the words I want to say here is, once you get either one of the one-sided limits being some sort of infinity, that means we have a vertical asymptote. Now, do I take the limits to find the vertical asymptote? No. I look at the function and I see where the denominator is 0. Like, oh, I have a vertical asymptote there. But if I was asked to just find a limit, for example, don't worry, we'll come back to the horizontal asymptotes. I haven't forgotten about them. If someone said, find the limit as x approaches 5 of, I don't know, 9x over x minus 5 to the second. Well, for any kind of limit where I'm not sure if the left and right hand side are the same, which I'm definitely never sure for one like this where we're divided by 0, I'm going to look at the left and the right hand side limit. Something like the limit as x approaches 5 from the right of 9x over x minus 5 squared. And then I see that on top, so when it's somewhere where it's not just 0, I'm just going to plug in the number and not something close to it. Like I'm not going to plug in 5.1 or 5.001. I'm just going to plug in 5 and say that 9 times 5 is 45. Now the denominator, I am thinking, okay, it's a number slightly bigger than 5. So a number slightly bigger than 5 minus 5 is a number that's slightly positive. And then it's getting squared. So I have a positive over a positive, which means I've got infinity. And then for the left-hand side, I approach 5 from the left of 9x over x minus 5 squared. Top's still going to be 45. But now the denominator is going to be a number slightly smaller than 5 minus 5. So it's going to be slightly negative. But it's squared. So even though the insides are negative, a negative number squared is still positive. I have a positive over a positive, which is still going to be positive infinity. So since the left-hand limit and the right-hand limit are the same, then we can conclude that the double-sided limit is infinity. And graphically, the difference here, and not that my graph is going to be perfect, but the graph of this function will look something like, at least around x equal to 5, what this pen is. Right, here a vertical asymptote at x equals 5. I feel like I just heard someone coming into class. I guess not. Okay, that's fine. Here, the limit as x approaches 5 from the right would be positive infinity, so it would do something like this. And from the left would also be positive infinity, so something like that. So here, the left and the right limits both go up to infinity. Whereas with the previous problem here, whatever this one looks like, I know that around x equal to 4, the limit from the right-hand side is negative infinity. So as I come at 4 from the right, it's going down to negative infinity. And then as I come at 4 from the left, limit x approaches 4 from the left, I end up getting positive infinity. So it'd be something like that. So that's kind of the difference. We haven't gotten to the horizontal asymptotes yet. We're about to. Before I say anything about the horizontal asymptotes, I want to say something about the vertical asymptotes. So what I want to say is, and it's kind of two things now. So if the limit as x approaches a of f of x is equal to some non-zero number over 0, So if that happens, there are two things to be aware of. Thing one, the limit is either infinity, negative infinity, or does not exist. And thing two, we will have a vertical asymptote at x equal to a. So again, let me say that one more time. If you're doing a limit and you plug in a and you get some non-zero number over 0, that automatically means we're going to have a vertical asymptote at a. And furthermore, the limit is either going to be infinity if they both go up to infinity, negative infinity if they both go down to negative infinity, or not existing if one goes up and one goes down like that. Are there questions about this? Yeah, of course. I'm going to go to the other side. But we can always come back to this. Okay. So now I'm interested in finding the horizontal asymptotes for f of x equal to x times x minus 9 over x minus 4. Which, if you recall, was x squared minus 9x over x squared minus 6x plus 8. And there's something not exactly. So it means. So let me kind of clarify because that's a good question. So kind of two different situations. If we have, let me see here. Yeah, let's just make it not super terrible. Let's look at the limit as x approaches. Sure. 2 of, sorry, I'm trying to make up something that's kind of nice here. Sure, that will be fine. Oh my gosh. X squared. Sure, yeah, plus, cool. All right, sure. Let's look at the limit as x approaches 2 of x squared minus 4 over x squared minus 5x plus 6 versus the limit as x approaches 3 of x squared minus 4 over x squared minus 5x plus 6. So either limit, I'm still going to try plugging in what x is approaching first. So if I plug in 2, here I get 0 over 0. 4 minus 4 is 0. 4 minus 10 plus 6 is also 0. You still could get a vertical asymptote here, but it's less likely. But the way we're going to deal with this is by factoring. So by factor, the numerator is x minus 2 times x plus 2. The denominator is x minus 2 times x minus 3. The x minus 2's cancel. And when I plug in 2, I get 4 over negative 1. So here, we just have a hole at the point 2, negative 4. In fact, I'll graph this for you guys. And I can graph it here in just a sec. Yeah, I can graph this. Yeah, sure. I can graph most of this, I guess. Whereas over here, if I plug in 3, I get 9 minus 4, which is 5, over, if I plug in 3 in the bottom, I get 3 minus 15 plus 6, which is also 0. So here, since when I approach 3, I'm getting a non-zero number over 0, we automatically know we have a vertical asymptote at x equal to 3. Now, I should point out, I haven't finished finding the limit here, right? I don't know if the limit exists and is some sort of infinity or is different from the right and the left. Here it is different from the right and the left. If I do, yeah, I can find it from here. I'm going to factor this. If I do the limit as x approaches 3 from the right of x minus 2 times x plus 2 over x minus 2 times x minus 3. Well, I can actually still cancel these, not that I really need to. If I plug in 3 from the right, top is 5, The bottom is positive. That's going to be a positive infinity. If I went from 3 from the left, those cancel. Now I'm getting 5 over a negative infinity. Sorry, a 5 over a slightly negative 0, which means I'm getting a negative infinity. So here, this limit does not exist because the right hand and the left hand limits are going to different types of infinities. One's going up to positive, one's going down to negative. But that still means we have a vertical asymptote. So if you do the limit and you get a non-zero over 0, guaranteed to have a vertical asymptote at whatever x is approaching. So yeah, we have a vertical asymptote at x equal to 3. What I wanted to point out is that if you were to graph this, so we have a vertical asymptote at 3. If we approach 3 from the right, we're going to infinity. If we approach 3 from the left, we're going to negative infinity. And we know that at 2, it would be equal to negative 4. But there's a hole at the point 2, negative 4. Because if you actually plug in 2, you get 0 over 0, which is undefined. So that's kind of the difference between a 0 over 0 type of limit often gives you a hole in the graph, whereas a non-zero number over 0 gives you a vertical asymptote in your graph. Correct. And so to clarify further, when I say this limit is negative infinity, it is actually still true that this limit does not exist. And because the limit isn't actually equal to a number. Infinity or negative infinity is not a real number. It's just that it doesn't exist in such a way that we can be more specific about. This limit doesn't exist, but I also know that it exists in a way where I know that as we get closer and closer to 3 from the left, that the function is getting more and more and more negative. So it's kind of a subtle distinction, but technically, right? So back on the other side here, oh no, sorry. So for example, if I said the limit, I know I did this one before, like limit as x goes to 5 of 9x over x minus 5 squared, right? We showed that the left and the right side for this one both were positive infinity. So even though we say this limit is infinity, technically it's not existing. It's just that we know that it's not existing in a way where both sides are going further and further and further up. Don't get too caught up about that. Yeah, so yes, but yes, if they're not the same, then it's definitely not existing. No, I'm not, so someone asked a question, am I saying the one-sided limits exist? I'm not saying that either. So so basically, if your limit is ever infinity, if it's ever equal to infinity, technically it doesn't exist. So if I said, right, the limit as x approaches 4 from the right of 2 over x minus 4, that limit would be positive infinity. We're going to write that, right, because it's going to be 2 over a slightly positive number. But in reality, it is also true that this limit does not exist, right? If I said, what's this limit? What's the number that limit is equal to? There isn't one. There is no specific number this limit's equal to. What we're saying here is that we know that as x approaches 4, this function gets larger and larger without bound. And then we happen to give it a name. So sorry, we're getting caught up in a very unimportant detail, but we've kind of gotten stuck. So I'm going to get out of it real quick. All we're saying here is that when you write a limit is equal to infinity, what you're really writing is the limit doesn't exist, but I know the function gets really large. Or if it's negative infinity, the limit doesn't actually exist, but I know that the function gets really negatively large. That's all you're really saying when you write this symbol for a limit. Hopefully that kind of clarifies things. Let's look at the horizontal asymptotes. Yeah. Oh, and I was going to say something else, which is that, So when you're finding vertical asymptotes for some things, or when you're trying to find vertical asymptotes, you typically want to factor as much as possible. This is the version I want to use of this function when I'm trying to find vertical asymptotes. If I'm trying to find horizontal asymptotes, it is almost always better to have the unfactored form. And in fact, I'm going to say this even more generally. If you're trying to find x things, meaning like x intercepts or vertical asymptotes, I know we're far from graphing, but this is going to come up later. You usually want the factored form. If you're trying to find y things, like the y-intercept or the horizontal asymptotes, you typically want the unfactored form. It's true. So if I'm trying to find the horizontal asymptote, well, the horizontal asymptote of a function is what you get if you take the limit as x goes to infinity or negative infinity of that function, if it's a real number. Right? If you get something like infinity as your answer, you don't have a horizontal asymptote. So there's a couple ways to do this. We don't have one of the tools, which is L'Hopital's rule. It's okay, we don't need it. So there's a shortcut way and there's a longer way. The longer way is to divide everything in your rational function by the highest power of x in the denominator. So in this case, we would divide everything by x squared. So limit as x goes to infinity, I have x squared over x squared minus 9x over x squared over x squared over x squared minus 6x over x squared plus 8 over x squared. And then we would simplify. So you end up with the limit as x goes to infinity of 1 minus 9 over x over 1 minus 6 over x plus 8 over x squared. And now here's the thing. As x gets really, really, really large, as x gets larger, larger, larger as it goes to infinity, what happens to 9 divided by a really large number? Does it get really large or does it get really small? It gets super small. So does 6 divided by x. So does 8 divided by x squared. So if x is going to infinity, any constant divided by x to a higher power, or just x to the first power, that's going to get very, very close to 0. So what happens is you end up getting 1 minus 0 over 1 minus 0 plus 0, which is 1. Now, the shortcut way to do this is to do the following. You look at your rational function, x squared minus 9x over x squared minus 6x plus 8. If the degrees are the same in the numerator and the denominator, right? The highest power, here the highest power is 2, here the highest power is 2. If the highest powers are the same, if the degrees are the same, then we say that the limit as x goes to infinity is the quotient of the leading coefficients. So in this case, the leading coefficients are both 1 and 1, so we get 1 over 1, which is 1. The highest power in the denominator, and we'll see why in the next couple examples. Yeah, that's an excellent question, Lauren. You can do the highest power anywhere, but there's one situation where that really just isn't what you want. So I will show you both those examples here just to kind of clarify. Now, I should also point out that in that previous example, if we take the limit as x went to negative infinity, we would get the same result, right? If x was to negative infinity, we're still going to have each of these things going to 0, and you're still going to get 1 over 1. Sometimes there are some weird ones where the limit to negative infinity actually is different than the limit to infinity. But I should say generally, to find a horizontal asymptote of a function, we find the limits as x goes to infinity of that function and the limit as x goes to negative infinity of that function. That's how you find horizontal asymptotes of a function. So let's look at something like, I want to find the horizontal asymptote of f of x equal to 3x squared plus 5 over 2x cubed plus 6x plus 1. In this case, just like before, I'm going to divide by the highest power of x in the denominator. So I'm going to divide everything by x cubed. So if I do that, to find the limit as x goes to infinity, if I divide everything by x cubed, I'm going to have 3x squared divided by x cubed plus 5 divided by x cubed. over 2x cubed divided by x cubed plus 6x divided by x cubed plus 1 divided by x cubed. That's going to end up equaling the limit as x goes to infinity of, let's see, so 3x squared over x cubed is 3 over x, and then 5 over x cubed divided by 2 plus 6 over x squared plus 1 over x cubed. And then all the things that are divided by x to a power, all of those are going to go to 0. So I end up getting 0 plus 0 over 2 plus 0 plus 0, which is 0 over 2, which is 0. So the second kind of rule, and we'll write this down in 1 second, is that if your degree on top is less than your degree in the denominator, the limit as x goes to infinity is going to be 0. And also the limit as x goes to negative infinity is also going to be 0. And then the last situation, which is, do I have enough room? Yeah. So let's say I want to find the limit as x goes to infinity of, sure, 4x cubed plus 3x plus 1 over x squared plus 5x plus 2. So here I do definitely want to divide by the highest power of x in the denominator. This is going to equal the limit as x goes to infinity of 4x cubed over x. So we could show this work every time, but I think I could probably cut to the chase and say, okay, if I divide everything by x squared, 4x cubed divided by x squared is going to be 4x. 3x divided by x squared is going to be 3 over x. 1 over x squared is 1 over x squared. And then the denominator, x squared over x squared is 1. 5x over x squared is 5 over x. And 2 over x squared is 2 over x squared. And now a bunch of things go to 0. But this 4x is going to infinity, right? It's 4 times something that's getting infinitely large. This is going to be 4 times infinity over 1, which is infinity. So if your degree on top is larger, you're going to get some sort of infinity if x is going to infinity. It could be positive infinity, but it could also be negative infinity. Like if I do the limit as x goes to negative infinity of the same thing, I'm going to cut to the second step here. If I've got 4x plus 3 over x plus 1 over x squared over 1 plus 5 over x plus 2 over x squared, well, now I've got these things still going to 0, but now I've got 4 times negative infinity over 1, which is negative infinity. Let me show you guys graphically, just so you can kind of really see what I mean. Sure. 1 moment. Just so you guys can see what I'm really talking about. If we were to graph something like this, sure. Whoops, that's not what I wanted. Come on. 4x cubed plus 3x plus 1 divided by x squared plus 5x plus 2. So you can see that. Can you see that? Let's zoom out a little. So looking at it currently, it looks like as we're going to the right, it's going up to infinity. And as we're going to the left, it's going up to infinity, which certainly seems to disagree with what I've got here. Let's zoom out. Did I write something stupid? No, it looks okay. There we go. Okay. So there was a vertical asymptote here that was making it go way up and then down. So as we zoom further out, we can see, oh yeah, as you go way to the right, the function gets infinitely large, right? The y values are really, really big. As x goes way to the left, the y values are very negatively large. That's what this is saying. As x goes way to the right, the y values are very large. I'm sorry, you guys probably can't see that very well. Right, here's what my board is showing. If x is going to the right, the y values are getting very positively large. If x is going to the left, to negative infinity, the y values are getting very negatively large. which is agreeing with what their graph is showing. So those are kind of the three options for a rational function. So in fact, we can spell that out real quick here. So if you're taking the limit as x goes to infinity of some sort of a sub n x to the n plus smaller terms over b sub m x to the m plus smaller terms. If the degrees are the same, right? If the degrees are the same, then the limit is equal to the quotient of the leading coefficients, a sub n over b sub n. If the degree on top is less, strictly less, the limit is 0. And if the degree on top is more, the limit is some sort of infinity. And it really depends on the difference in degrees and if you're approaching positive or negative infinity. So you have to be a little more careful with this last one. Okay, let me look at some of these. We've got 12 minutes left. Let me grab, yeah. So there were some questions people had. I feel like we should look at this graphing one first. No, that's that. We can save that one for next time. Sorry, there were a couple graphing ones, but they most more about continuity. Let's look at this one. Sure, I think this one is worthwhile to look at. So let me share this with you. Come on, share. What is going on? Oh, sorry. I see. Gotcha. All right. So if we look at this one here, it asks us some questions about finding the limit. So if we're trying to find the limit as x approaches 1, and I'm assuming the blue, oh yeah, the blue one's f and the red one's g. So, yeah. So the limit as x approaches 1 of f is certainly this value up here, which is 2. But it really, oh wow, I can draw on this. That's kind of cool. I want to make it absolutely clear. I want to delete those things that I really want to do. Okay, cool. So if we're approaching, if x is approaching 1, the y values are getting closer and closer to 2. Yes, we can all see that f of 1 is not equal to 2. F of 1 is equal to 0. It doesn't matter. Limit doesn't care what's happening at 1. It only cares what's happening near 1. So for this problem, I'm just going to write down real quick. I can see that the limit as x approaches 1 of f of x is equal to 2. Now for g of x, we've got a problem because we can see that for g of x, the left-hand limit is 0 and the right-hand limit is -1. So the overall limit does not exist. All right, let me write that down too. Limit as x approaches 1 from the left of g of x is in fact 0. And the limit as x approaches 1 from the right of g of x is in fact 1. And when the left-hand limit and the right-hand limit aren't the same, we end up getting non-existence. So that means that the limit as x approaches 1 of f plus g also does not exist because one of them doesn't exist. What about as x approaches 2 here? Well, again, if we look at the graphs, here's 2. For f as x approaches 2, the limit's going to be 1. For g as x approaches 2, the limit's going to be 0. 1 plus 0 is 1. And then we can do this. So basically, you're finding the values for each of them. So the only one that's a problem here is the one at 1 because it doesn't exist, because this limit as x approaches 1 of g doesn't exist. All the rest of these work out to be okay. Here you just multiply them together. Here you divide them together. Here you have to figure out what f of x is. So for like this last one, as x approaches -1, which is right here, the f value is approaching -2. So if you plug in -2 for f, you get 3 plus -2, which is 1, and the square root of 1 is 1. So this last one should be 1. I think the rest of them are all right. Yeah, so I'm pretty sure whoever asked me this question, it's a good question. I'm pretty sure you had it all correct, except for the very last one should have been not that. It should have been the square root of 3 plus -2. Good question. But again, I want to really emphasize here that when you're talking about limits, you're talking about what is happening to the graph or to the y values of the graph as the x values get closer to the one in question. So especially for this one right here, the y values are getting closer and closer to 2 as the x values get closer and closer to 1. Yeah, let's look at this one. This is a good question. Let me write this one down. I got 2 more limits I can go with. This is warm in my office. Also, it is super windy in Woodland today. It was also super windy in Woodland yesterday. For a run, it was hard. Let me stop sharing my screen, guys. I'll try this question. So here's our function. This is definitely the style of function that we're going to look at when we start talking about continuity. So -1 minus x plus 2 for x less than -2. And then we've got 2 when x is equal to -2. And then we've got 3x plus 9 when x is bigger than -2. And this is definitely asking us each side. So if I want to find the limit as x approaches -2 from the right of f of x. So if we're approaching -2 from the right, it means we are bigger than -2. When we're bigger than -2, the function is equal to 3x plus 9. So for this limit, we're just finding the limit as x approaches 2 of 3x plus 9. And then, since it's not a 0 over 0 or division by 0, we can just plug in -2. So I plug in -2, I get 3 times the -2 plus 9. Don't pick some other number that's like close to -2 to plug in. We really just get to plug in -2. So 3 times -2 is -6 plus 9 is 3. On the other side, the limit as x approaches -2 from the left, now we have to use the piece of the function where x is less than -2, which is up here, which is this part right here. So it's going to be the square root of -1 minus -2. Oh, sorry, one extra step. It's the square root of -1 minus x. And then I'm going to plug in the x is approaching -2. So I'm going to end up getting, I feel like, oh, I forgot the plus 2 here, sorry. So it's going to be, yeah, the limit, sorry, I'm plugging in, which means I don't write the limit anymore. So I'm going to get the negative square root, sorry, that negative is the superscript there. There's a negative out here. There's a lot of negative signs flying around here. -1 minus, I'm plugging in the -2 for x. Feels like it's wrong. Oh no, my brain is just having a hard time. Plus 2. -1 plus 2 is 1. Square root of 1 is 1. So I get 1 plus 2, which is 3. Okay, so the left-hand limit is 3. Sorry, the right-hand limit is 3. The left-hand limit is also 3. So that means that the overall limit has to be 3. So the limit as x approaches -2 of f of x is equal to 3. Even though f of -2 is equal to 2. That's kind of the whole point of this question, is that since the limit from the left and from the right are the same, the overall limit has to be whatever that value is. Okay. And then let me see. Let me do, sorry, before, don't take off yet because we're still 5 minutes. Also, let me capture the attendance real quick just so I can enter it later. I think that was everyone. Cool. I think I got everyone. Okay, cool. Yeah, there are a couple. Yeah, these questions are good. So sorry if I didn't get to everything today. There's so many things to say about limits. Let's do another limit to infinity, specifically this one. The limit, I'm going to do the negative infinity one because this is the one that's more interesting. But there's actually 2 questions here. The limit as x goes to either positive or negative infinity. The square root of 3 plus 5x squared over 8 plus 2x. Okay, so here's the idea. This is very similar to the rational functions ones where we divided the top and bottom by the highest power of x. So like, for example, if I was doing the limit as x goes to negative infinity of, 5x cubed plus 6 over 3x cubed plus 7x plus 1, I would divide the top and bottom by x cubed, and then we would find that the limit was 5/3. We're not going to do that one, but that's the kind of point. We're dividing by the highest power of x in the denominator. So I'm going to divide the top and bottom by x to the first. So check this out. Now, people kind of do this a little bit. I'm kind of going the long way here to kind of show you what's really happening and to answer the question that was asked. Because the question that was asked is, why do we divide by something different in the square root? Well, here's why. So I'm going to divide. That's an interesting question. Yeah, it's going to be a little bit complicated. So dividing the bottom by x. I'm also dividing the top by x. Now the problem is, to be able to simplify this, I really need to kind of get that x inside the square root there. So what I'm actually going to do is I'm going to rewrite that x. Now this is where things are going to get really kind of iffy. I'm going to rewrite x as the square root of x squared, although it's technically not. And here's, let me say this here. So I'm going to rewrite this. Actually, I'm just going to erase this. And then I'm going to kind of, well, I'll go back around. So x is normally the square root of x squared, except it's not in this case. It's actually the negative of it, because x is approaching negative infinity. So let me tell you guys this. X is equal to the square root of x squared if x is positive. Right? If x is 9, the square root of 9 squared is 9. But if x is negative, you can't just do that, right? If x is negative 9, the square root of negative 9 squared is the square root of 81, which is still positive 9. So the square root of x squared, you have a negative in front of it to make it turn into a positive. Sorry, to make it turn into a negative. So if x is negative, x is equal to the negative square root of x squared. Why does it matter? Well, because x is negative, because it's approaching negative infinity. So here's what we're going to do. We're going to write this as the limit as x goes to negative infinity of the negative square root of 3 over x squared plus 5x squared over x squared over 8 over x plus 2x over x. So that might seem kind of funky, but that's the way it kind of works. There are other ways to kind of start off, but this is what we want. And now look what happens. The x squareds cancel. The x's cancel. 3 over x squared goes to 0. 8 over x goes to 0 as x goes to infinity or negative infinity. So you end up getting negative square root of 5 plus 0 over 2. Okay, let me do the other half of this problem to kind of show you guys how this usually is more normally done. Yeah, let me erase this. I know we're like out of time. So let me do the other half just so I can kind of show you guys the more normal way of doing this. But if you gotta go, you gotta get. So here's the more normal way of doing a problem like this. I wanted to find the limit as x goes to infinity, positive infinity this time, of the square root of 3 plus 5x squared over 8 plus 2x. What people often do instead of dividing by the highest power is they factor out the highest power. So in the denominator, I'm factoring out an x. So I'm left with I'm factoring out x, and I'm left with an 8 over x plus 2. Now, in the denominator, I factor out an x, so I'm going to try and factor out an x in the numerator. But the thing is that inside the square root, x is like the square root of x squared. So I'm going to factor out an x squared from there, and I'm left with a 3 over x squared plus 5. And if we multiply the x squared back through, we get 3 plus 5x squared. Now here's the thing. This is equal to the limit as x goes to infinity of the square root of x squared times the square root of 3 over x squared plus 5 over x times 8 over x plus 2. And this is where things get funky. If x is positive, then this is just equal to x. But if x is negative, this is equal to negative x. So this is the step where it kind of depends on if x is approaching infinity or negative infinity. In this case, since x is approaching infinity, we would rewrite this as the limit as x approaches infinity of just x times the square root of 3 over x squared plus 5 over x times 8 over x plus 2. Then the x's cancel, and then this goes to 0, this goes to 0, and you're left with the positive square root of 5 over 2. So typically for ones like this where you have a square root of x squared, the limit to infinity and the limit to negative infinity end up having the opposite sign from each other, which means this function would have two different horizontal asymptotes. Negative square root of 5 over 2 to the left and positive square root of 5 over 2 to the right, which is kind of weird. Hopefully that makes some sense. We'll continue talking about limits on Thursday, and we'll probably start talking about continuity as well.